Hello everyone. Today in this video we'll be covering the chapter of carboxylic acids and esters, which is basically a part of organic chemistry. Now, reaching towards the end of organic chemistry, this is a very important topic. To begin with, we should know that the general formula of a carboxylic acid is CnH2n plus 1 COOH. Now, to see how this general formula is applied, the first acid in the series is called methanoic acid, and it is a 1 carbon acid. Its formula is this. Now, one very important thing to note over here is that the COOH is consisting of a C double bond O and a C single bond OH. Okay, so that's very important. Now, this is when N is equal to 0. That's important to consider. Now, after that, we have to look at the second acid in the series to see how this progresses, which is called ethanoic acid. Now, the formula for that is when N is equal to 1. So generally, if you just put in the value, you would get this. Now, eventually, with much practice, you will get used to this entire naming and drawing process. Now, moving on. One more thing to realize is that in carboxylic acids, the first carbon, 1 carbon carboxylic acid till the 9 carbon carboxylic acids, they are all liquids by nature. Their states are liquids. Okay, and when the carbon chain keeps on becoming longer, when the carbon chain is more than 9 carbons, they become more compact and they become white crystalline solids. So these are some important general properties to know. Now, moving on, the physical properties of a carboxylic acid. Now, the first physical property that we will be considering is called solubility. Since carboxylic acids have strong intermolecular hydrogen bonds, they are extremely soluble in water or polar solvents. Now, let's look at how hydrogen bonding exists in carboxylic acids. Over here on the screen, I have drawn two molecules of ethanoic acid. Now, we know that hydrogen bonding exists when the lone pair of oxygen, fluorine, or nitrogen attaches itself with hydrogen, right, of another molecule. So let's look at this now. We can clearly see that the oxygen over here would have two lone pairs, and that would basically form a hydrogen bond with this hydrogen, and the oxygen over here also has two lone pairs, and that would form a hydrogen bond with this hydrogen, right? And we obviously have to put the dipoles. So this would have the delta negative, this would have the delta positive, delta negative, and that is due to the difference in electronegativity, which was covered in a previous video. Again, over here also. Okay, now moving on. We know that solubility is extremely high, but one thing to note is that the solubility of carboxylic acids decreases as the number of carbons increase. Why is that? Let's understand this. It is because the polar part of a carboxylic acid is only the COOH part, right? But as the carbon length gets longer, the COOH part does not dominate anymore. The ID forces, or the induced instantaneous dipole forces of the carbon and hydrogen chain, which is non-polar, that dominates, and therefore solubility overall decreases. This is as simple as it is. So this pattern is one that you need to know. Now moving on, we will now study the preparation of carboxylic acids. First of all, the first two preparation methods include oxidation. Now, oxidation of what exactly? The first method includes oxidation of primary alcohols. This is signifying primary alcohols. The first primary alcohol that we know of, or we could use as an example, as I have over here, is ethanol, right? Now, we should write down the conditions. The conditions are an oxidizing agent, which is acidified potassium dichromate in this case, and heat will be under reflux. Now, continuously heating this and with the presence of acidified potassium dichromate, ethanol will be oxidized and it will form a carboxylic acid with the name of ethanoic acid. One thing to note in this is that the carbon chain remains the same from reactants to products, meaning that there are two carbons in the alcohol of the primary alcohol that we've used as a reactant, and there are two carbons in the product carboxylic acid that we have. So one thing to realize, a very simple thing, is that whatever you do, the product must have exactly the same number of carbons as that of the reactant. Okay. Now the second example that we'll be doing is that of oxidation of aldehydes. Now aldehydes have been covered in another video, and the chemistry of aldehydes has already been discussed in that. Over here we'll be covering one reaction from that extensive chemistry, which is that of oxidation of aldehydes. Again, the conditions remain the same. We will be using acidified potassium dichromate and heat will be under reflux. These conditions are extremely important. You cannot forget them. Again, over here also, a 2 carbon aldehyde is changing into a 2 carbon carboxylic acid. So one thing to remember again is that the length of the carbon chain does not change. Okay. Now moving on to the next methods of preparation, which include hydrolysis. Hydrolysis basically means to remove a water molecule in a sense. Now, it has many other meanings also, but that is what will be discussed in the first one. In hydrolysis, we can see that there is a hydrolysis of nitrile going on, right? Now, hydrolysis of nitrile has a very specific condition, which is that it must be acidified. This is an acid hydrolysis of nitriles, and heat must be under reflux. Now over here, again, a very important thing to consider, that the length of the carbon chain of the nitrile is 2, right? And the length of the carbon chain of the carboxylic acid that is being formed is also 2. So again, the carbon length of the chain is not changing. Okay. Now, hydrolysis of esters. Esters and its chemistry will be discussed in a later video. So if something is unclear at the moment, don't fret, it will be cleared out. Now this is an ester. An ester is a chemical compound that has the COO group in it. This is what makes it an ester. Now what happens is, in hydrolysis of ester, first of all, the reagents are the same as that of hydrolysis of nitriles, heat under reflux and acidified. Now over here, from prior O-level knowledge, we know that this is the acid part of an ester and this is the alcohol part of an ester. By hydrolysis, this C single bond O breaks up and water is added across these two bonds, and that forms an alcohol and a carboxylic acid. This must be confusing right now. We will discuss the chemistry of the hydrolysis of esters in a later video. So in all of these 4 reactions, we can see that we are getting a carboxylic acids as a product or a byproduct, and that is all that we are concerned with. This is all that there is for this video. Thank you.